Okay, let's start. Do you have any questions? All right. So the second midterm is going to be next Friday. So the topics will be, right, everything after the first midterm until today's content, which roughly will be these things, American options, um, American games, right? Games with optimal stopping. So Brownian motion and its properties, Ito integrals, okay, and properties, Ito's formula, Black-Scholes model, right? I guess S here because it is different version, and Black-Scholes formula, which we'll talk about today. Okay, so this will be the topics for the exam. The format of the exam is exactly like last time. The two differences is that one, submit your formula sheet with your exam. And two, we won't use Proctor Track, but we'll use Respondus. It's a new software that the university requires, and is similar, but like to Proctor Track, I think, but there's a difference where it has a locked down option. Or actually, it is a must. You have to have your browser locked down, which may create some issue with submission by file. Okay. So what I'll do is I'm gonna ask you to practice for your quiz. Okay. With responders, so you see what it's all about and what you need to do with it. For the exam, what I'll do is I'm going to turn it on for the first portion of the exam, and I'll turn it off for the last 15 minutes or so that you can you can submit whatever you need to submit. So but you still need to use responders for your first duration of the exam. So if you don't practice, you won't be able to kind of know what it's all about, and you may run into issue if you use it for the first time for the exam. Okay. So for the quiz, I anticipate the same problem that you may not be able to submit. So for that, I will turn it off, let's say on Monday morning. I suppose that a lot of you do quizzes on Monday anyway. So for that reason, do not try that this time, okay? Because you won't be able to practice with the responders. So you should. Any question on these? All right. So to continue with where we left off last time, So last time we were discussing, right, the three variations of Black-Scholes model, which is this mu st dt plus sigma st dwt. This can be viewed as the model for percentage return. Because if you divide by st on both sides, you get the model for percentage return. You get the percentage return. Then you get the log return, which is mu minus 1/2 sigma square dt plus sigma dwt. So it's log return. And finally, we also get the model itself, the explicit formula for st. So st will be e to the s0 e to the r minus 1/2 sigma square times t. Okay, let me write down. So exponential of r minus 1/2 sigma square times t plus sigma wt. Okay, these are three versions of the Black-Scholes model that can be shown to be equivalent by the Ito's formula. All right. So we also mentioned, right, the models for interest rate, which is basically kind of discussing why, these formulations are important rather than the explicit formula, because these are the differential formulation, like the derivative formulation, while this is the explicit formulation of the stock price. So the model for interest rate has two types, the Vasicek, where we say that dRT is mu minus RT dt plus sigma dwt. And we have the CIR model, where we say dRT is plus sigma square root RT dwt. Okay. So let's try to kind of see the point of these models a little bit. And several things. Vasicek model has an explicit solution, while CIR does not. So that explains why we do not always need to have an explicit formula for a model, but having a dynamic, okay, the differential formulation is good enough. Vasicek, the interest rate in Vasicek can be negative, while the interest rate in CIR will always stay non-positive, non-negative. All right. So I'll remark on some of these, and probably the rest will leave you for the homework, because the focus for today is to work with the pricing, okay, for the Black-Scholes model, Black-Scholes formula. Okay, so on this part, right, why does CIR model have an explicit solution? So explicit solution for CIR can be obtained like this. Oh, sorry, Vasicek, I'm sorry. The explicit solution for Vasicek model can be obtained by looking at the differential of e to minus mu t times RT. Okay. Wait, hold on. I'm sorry. The differential of e to the t, sorry. e to t RT. Okay. And if you do this, you will see that if you differentiate this, right, using Ito's formula, you will see that this differential, the right-hand side, does not depend on RT. So in other words, if you do this, then the right-hand side does not depend on RT. So you got rid of the RT, so you can integrate both sides because this is a differential, right? You can then integrate both sides. And solve. Okay, that's how you can do it for the Bessy-Check model. For the CIR, you cannot do so. Even if you do that, the right-hand side still depends on RT. And the reason is this term right here that spoils it for you, okay? This square root terms right here, that spoils it for you. So that's why this trick would not work. Well, that doesn't show that CIR does not have a solution, okay? To show that something has a solution is kind of weird. To show something has a solution, you just have to exhibit the solution. To show something doesn't have a solution, somehow you have to show no solution would work, but how would you do that? But at least we can show that the same trick, right, does not work in the CIR case. So you kind of appreciate that it's not something trivial. Okay, so you'll be asked to play with, you'll be asked to play with this, okay, on the homework. Now, for the second point, which is that Bessy-Check can be negative while CIR doesn't have to, right? Let's see what happened. Both of these models are so-called the mean reverting model. What does it mean? What it means is this. If you focus only on the dt term, you see that if the interest rate is below a level mu, then this term will be positive. Okay, so if RT is below mu, then mu minus RT is positive. If RT is bigger than mu, then mu minus RT will be negative. So you have, right, DRT, the change in the interest rate, is mu minus RT dt plus something else, dWt. So first of all, right, if you ignore the effect of the noise, if you ignore this for now, then what you see is, right, if you are below, this pull you up because it's positive. If you're above, this pull you down because it's negative. So therefore, right, it reverts back to the mean level mu, whatever that is. That's like the generic level of the interest rate that we observe. Okay, so that's why it's called mean reverting. On the other hand, right, this noise kind of adds the stochastic component, adds the the random fluctuation to this trend of mean reverting. If you only have this, then it's going to be a very, very nice solution going down to mu or going up to mu like that. As a differential equation. The Brownian motion component brings the fluctuation to the movement of the interest rate. So now if you take a look, right, the Bessy-Check fluctuation is just purely a volatility component multiplied with the Brownian motion noise. So if you kind of take a look and think about suppose you have interest rate, right? Suppose you start here, and suppose that this is the mu level. So in general, your interest rate should drift to, okay, the level mu in the long run. So this is R. This is your R0. But suppose that for some reason your interest rate quite low right now. Then what it says is with a shock, with a market shock, right, in the wrong direction, meaning in a negative direction, and with the volatility level, it could drive your interest rate down to below, like that. So that's exactly what could happen with the VASI check. Okay. On the other hand, what about CIR? With the CIR, there is a square root term of the RT right there. So what happens is this. You could have a very similar story, okay? Starting from R0. General tendency is to go up to mu, but somehow, right, you have a shock when your interest rate is low. Except that, right, we know that this is a continuous curve. It's a continuous interest rate curve. And so it must cross level 0 at some point if it's on its way to be negative. On the other hand, if it touch level 0, right? So for CIR, for RT is equal to 0, then this whole term is equal to 0. Okay, so basically the moment you touch 0, magically the noise components turn off. But if the noise components turn off, then what you have left is only the first component. Or rather, right, because RT is 0, it's just this component, which is entirely positive. So it will entirely pull you up. So the moment you touch 0, the CIR model say you will immediately get pulled up. Okay, so for that reason, the CIR interest rate will never go below 0, because when it hits 0, there's no noise. The noise components turn off, and then it will get immediately pulled back up by the DT component. All right. So that's the explanation for this part. So notice, right, one thing I just want to mention is the reason why I bring this up is A, right, these models we'll see later on when we look at interest rate models. But B, they demonstrate that, right, so far my arguments are basically all based on the differential ideas. I'm discussing how the interest rate changes as time change, that kind of thing. I never bother, right, with the explicit formula of RT. As I said, that's more, that's more complicated than not. It doesn't tell me how things move, right? When I was investigating how the interest rate moves as time moves, exactly this is the idea that I need to use. Okay, and that's the demonstration. Any question? Okay, so now let's go back to the Black-Scholes model and discuss pricing. Okay, so Black-Scholes model again. Let's do, for this time, let's just focus on the percentage return and the explicit formula. We won't mention the log return. Okay, we want to discuss, right, with pricing, we want to discuss, right, the central idea behind pricing is we need to have a risk neutral model. So we need to discuss physical versus risk neutral model. So recall, right? This is where all our abstract discussion before will be helpful. That the risk neutral model, whatever it is, must satisfy this. In other words, whatever the model is, right? When you take expectation under that model, the discounted stock price must be the initial stock price. Or actually, more generally, okay, if you have a multi-period model, or if you have, if you have a multi-period model, or like basically you have more time, right? Then for U bigger than T, this must be ST. Sorry, so this is discount only from U to T, like that. Okay. So if the model you pose do not satisfy this, then you're not under the risk neutral model. So here, right, the point I want to make is, and I think we said this before, this is not a risk neutral model unless mu is equal to R. Okay, so this is not risk neutral unless mu is equal to R. Okay, so the understanding, okay, is mu is the average return of the stock. Okay, or well, the average percentage return, right? You see, the average percentage return of the stock, right? And sigma is volatility. So obviously, we're not saying that the average percentage return is just the risk-free interest rate. We're not saying that. We're saying though that you must find a probability so that under that probability, okay, that's a different worldview. That's a different weighting of the risks. All right, just like the tree, right? It's a different weighting of the U and D, up and down. So here is a different weighting of the risk, so that a weighing of the risk, right? So that under that weight, okay, under that weight, the percentage return of the stock is equal to a risk-free rate. It's kind of weird, but you know, that it's not that strange, because if you remember, this is the same exact idea as when we look at expectation of what was it? So when you look at up times Q, right, plus D times 1 minus Q, this must be E to R delta T. You have seen this calculation before in the binomial, in the multi-period binomial model. Okay. So here, what does this equation say? This equation says, right, that U and D, right, are basically the return, right, of the stock, roughly, right, roughly the return of the stock under the up and down scenario. Q and 1 minus Q, though, right, are the weights under risk neutral framework. And you see, when you average them out, it's exactly the same as the risk-free rate return. So that's what I mean, right? So we're not saying that it's actually the risk-free, but if you weight them in the risk-neutral framework, then it must be equal to. All right, we'll make it clear later. But so let's demonstrate, right, this calculation that to show that it's not risk neutral. Okay. So I will do expectation of ST, right? Discounted stock price, which is expectation of e to the r minus 1/2 sigma square t plus sigma wt. And as you can see, right, at S0 goes out, you got this cancel with this, and e to the minus 1/2 sigma squared t goes out, and you only have e to sigma wt. We have done this calculation before. This uses the moment generating function of the normal, and this will give you exactly 1/2. Oh, what am I saying? I apologize. This is not r. Exactly when it's r is canceled. This is mu, right? This is mu because of this. This is mu. So mu. So sorry, right? And so exactly it doesn't cancel, but it will give you e to the mu minus r times t, right? And so it will give you e to the mu minus r times t, and the final answer is e to the mu minus r times t, all right, which is not equal to S0 unless mu is equal to r. So that's why, right, when this guy right here is mu, it is not risk neutral. Okay. Any question on this? All right. So then obviously then you ask, well, so how do we work with a risk neutral model, right? So let me look at the percentage return for now. It may be very tempting, and I don't know, you may see it elsewhere if you don't pay attention. You may see something like this. Basically, right, the whole point is, well, you say, unless this is R, right, it won't be risk neutral. So yeah, go ahead and replace this with R. Or another way to do this is, you know, again, right, you just do this. You just replace mu with R. Okay. So on some level, this won't do much harm because the calculation is done in the same way, but conceptually it's wrong. All right, conceptually it's wrong. And conceptually it's wrong because this is the same Brownian motion you are indicating by using the same letter. Is not the same Brownian motion when you go from the first to the second model. All right, so there will be a different Brownian motion under the risk neutral framework, a different Brownian motion under risk neutral framework, and W tilde is not W. And this justifies why I use the notation E tilde when I refer to risk neutral calculation, right? In the tree, in the binomial tree, E tilde kind of says that we use Q and 1 minus Q in our calculation. In the Brownian motion framework, right, in the Black-Scholes framework, the E tilde exactly refers to the fact that we use Brownian motion as W tilde instead of W. Okay. So let me explain how formally to go from here to here. To go to go from the first physical model. So this is physical, right? And this is risk neutral. To go from the physical to a risk neutral model, you basically play the game of add and subtract R. If you add and subtract R, right, you got mu minus R. Okay, now you group. So sigma. And this guy right here is what we call the W tilde prime motion. Okay, so that's why they're different. The W tilde is the original prime motion plus mu minus R over sigma times T. Okay. And this is more than just a mathematical curiosity, by the way. Okay. This is not just mathematical curiosity. This has a name. This quantity is so important, has a name. It's called the Sharpe ratio. In fact, is very popular in investment. When looking at a company, people don't generally care for the return, but they care for the Sharpe ratio. The reason is, right, first of all, it's not just the return, but the excess return, the return with respect to risk-free, because a company is expected to earn above the risk-free. So if you don't earn that much above the risk-free, right, so your return should be measured against the risk-free. But also, your return should also be measured against the risk level that you are, exposed to. If you earn a lot of return with a lot of risk, that's not too spectacular. So that kind of punish, okay, if you cannot bring it down, if you have a lot of risk. So anyway, right, all in all, a high Sharpe ratio is a good performance, and a low Sharpe ratio may mean, right, should mean a bad performance in terms of risk balancing, right? Some people obviously still prefer high risk, high reward rather than low risk, low reward. But right, all in all, everyone should agree that, right, that higher Sharpe ratio is going to be better than lower Sharpe ratio. Anyway, right, the point being is you see that converting from the physical model to the risk neutral model exactly brings out that you embed, right, the drift that is the Sharpe ratio of the company into the shock, right, into a shock, and you hide it and you call a different component. So it's like exactly you take away the Sharpe ratio component of the company, it basically, right, only returns to risk-free rate. Okay, so that's the thing. And obviously, right, so second thing is this. I hope it's obvious. Obviously, W tilde is not a Brownian motion under the physical framework. Why? Because WT is a Brownian motion under a physical framework, and this makes the mean, the average, no longer zero, right? It's a Brownian motion with drift. It tends to go up. Brownian motion must always have mean zero, right? So simply because expectation of W tilde is this, is not zero. So if something has expectation non-zero, it's not a Brownian motion. Okay, I mean, among other obvious properties. So What that means is you need to somehow find a different weighting, okay, different framework that somehow that you can view this guy as a prime motion. So there is a way to do that, which is beyond this class. It is a treatment requires some kind of measure theory, graduate measure theory, or exposition to measure theory technique. So basically, I'm just going to mention that there is the way to find the appropriate framework to view W tilde t as a prime motion is called the Gersanov transformation. Okay, I'll just mention that. So basically, there is a way, okay, a mathematically rigorous way to do so. We do not do that. We accept that there is a way, and exactly that way is expressed by us by the notation E tilde. All right. So under the framework E tilde, okay, or under P tilde, whatever you want to call it. So we accept this. Under P tilde, W tilde T is a prime motion. So again, needless to say, under P tilde, WT is not a prime motion. So P tilde is the Ritz neutral framework. Under P, WT is a prime motion. W tilde T is not. Okay. And the relation between the two is right here. So from here, right, you can switch back if you want to find WT from W tilde T, right? Any question? All right. So now for the pricing purpose, right, we can just start from the Ritz neutral framework. In other words, we'll say that dst is r st dt plus sigma st dw tilde t, or st to be s0 e to the r minus 1/2 sigma square t plus sigma w tilde t. Okay. So that's it. We will accept that there is a way for us to do so, and we'll just do it. Now, then we want to price a call option on S with exploration T and strike K. All right. And so what that means, right, is we have the call option whose value at time t, big T, is st minus k plus. By the Ritz neutral pricing formula, you get, so first of all, the formula is this, right? V0 is E tilde e to minus RT st minus k plus. But that's an abstract formula that holds for any model, okay? Our interest here is to express this in terms of a function, right, of, a function of r sigma k t, etc. And that, the way to do that, right, or that formula, is exactly the so-called Black-Scholes formula. It says this whole thing is S0 ND plus minus K e to the minus RT ND minus, where D plus minus is R plus minus 1/2 sigma square times T minus natural log of K over S0 divided by sigma square root of T. And the notation n of x is very popular in finance to denote the CDF of the standard normal. Okay, so this right here is the Black-Scholes formula. Any question on this? All right. So the Black-Scholes formula probably is, looks scary and involved. But first of all, right, this is probably the #1 popular formula out there in the, finance world, where, right, you walk around and even people who are not super involved with all these things will be aware of the Black-Scholes formula. Okay, it's that popular. And so, yeah, memorizing this kind of thing and beyond is not totally out of the question, really. Obviously, the first time you see it, you won't memorize it right away. I'm just saying that if you somehow have something to do with this field a lot, this you will see in, day out. All right. What do we want to say here, right? So first, we want to show why this is true, right? So proof, and then extend this to the VT, right, value of the option at time t, extend to put option, and then interpret some terms. In particular, the ND plus, ND minus that I want to explain, okay? So they have some financial meaning. All right, okay. So, and after we finish with this, I think we can call it a day. And here, right, is the end of the material for the exam. I mean the end, the cap. So first, right, how to prove the Black-Scholes formula. How to prove is, if you really are not prepared for this, then what you need to do is to take this expectation, right, where, remember, because ST, right, is S0 e to the R minus 1/2 sigma square times T plus sigma WT. WT, right, is a normal 0T. You could view this as S0 e to the R minus 1/2 sigma square T plus sigma square root of T times Z, right? And so if you want, you could do this, the integral of e to minus RT S0 e to r minus 1/2 sigma square t plus sigma square of tx. X here being the representing the, or you can call it little z if you want. Doesn't matter. Let's call it x, right? Represent the standard normal, and then times the density of the standard normal. Sorry, there's a minus k plus, right? Like that. Okay. So right here is st minus k plus. This is the density of the standard normal, and then you just compute that. But this, like I said, I think I mentioned at one point, this is super painful, and you definitely do not want to start here. You want to do some simplification if possible, okay? And in fact, if you recall in your homework, you were asked to do a similar expression. And so we will piggyback on that. All right, so from the previous homework, let me look up that and tell you precisely why it is. From your previous homework. So let me see here. I think homework 8. Yeah. Homework 8, problem 1. So in your homework 8, problem 1, you're asked to prove that expectation of e to wt minus k plus will be equal to e to t over 2 n of t minus natural log of k over square root of t minus k n of minus natural log of k over square root of t. All right. And for the full proof, of course, see the solution of that homework. But that is the result. And it's not that bad, okay? The point is not that bad. Now, notice, right? First of all, you see this is exactly motivated by that, right? Where obviously this is the simplified version of this. And so the advantage is that we take out all the bells and whistles and we just focus on what's essential, which is the Brown motion component, and derive this form. Now to put everything back, right, to, of course, the model, then we just have to relate. We just have to relate the ST here, right? Or we just have to somehow reduce this expression to this expression and then use the formula. All right. So now we need to connect and so by the way, right, even though in that homework problem, this is E, right, and this is W, you see, obviously, this also works because it's the same Brown motion. I mean, it's a Brown motion, right? So whether you calculate under the Brice neutral with W tilde, the physical and with W is the same thing. So we need to connect this with E of, right, E to minus R T st minus k plus. Okay. So how do we connect it? We connect it like this, right? That basically ignore this for now. Ignore this for now, because it's a constant term. Okay, we can multiply it in after we finish our calculation. The term of interest is st minus k plus. And we want to exactly compare this with this one. So st minus k plus is S0 e to the r minus 1/2 sigma squared t plus sigma wt minus k plus. Now here's something. Claim. If you have a constant times x minus k plus, it will, and you want to factor out that constant, you can. All right. So the plus function, even though it's nonlinear, right, it works okay with constant factorization. All right. Why? You just have to look at the case when it's positive and it's negative. If cx minus k is positive, right, then that means that cx minus k plus is equal to cx minus k, which is equal to c times x minus k over c. But cx minus k is positive, obviously is the same as saying that x minus k over c is positive, because c is positive. So this is, of course, equal to cx minus k over c plus. But when it's negative, then again, right, it's the same thing happens because, right, and so they're both equal to 0, and so you're good. Okay, so the whole point is you can factor a constant out of the plus function. Any question? So what is the constant we want to factor out? The constant we want to factor out is this whole thing right here. We want to factor out this whole thing right here. Okay. So basically then, st minus k plus will be a constant times e to sigma wt minus k tilde plus, where the constant will be this thing, and k tilde will be k over c. All right. Sorry, w tilde, right? Did I do that? W tilde. All right. So it seems like now we can calculate then just this using our formula. But there's still one minor detail, right? One minor detail is our formula say is w tilde t. Well, here we have something in front. We have a sigma in front. Okay. How do we fix that? Well, the second fix is easy because basically, remember, w tilde t is a normal 0t distribution. And in this calculation, it's only the distribution that matters. It's not about w or not w. And so sigma w tilde t will have a normal 0 sigma squared t distribution. Okay. So in other words, right, this expression is the same as saying you replace t with sigma squared times t. Okay, you replace t with sigma squared times t. Or if you will, at the risk of being a little bit dramatic, it's going to be w tilde sigma squared t minus k plus. Okay. Sorry, e tilde, right? Is that okay? Now, again, right, pay attention. I'm not claiming that this is equal to that. I mean, without expectation, right? I'm not saying this sigma w tilde t is equal to w tilde sigma squared t. I'm not saying that at all. I'm saying after you take expectation, right, on average, in terms of a number, then these guys are equal. Because the average doesn't care, right, about the actual value of these guys, only care about the distribution. And the distribution of these guys are the same, namely this. All right. So it's with this form that we can apply our formula. Sorry, I forgot the tilde, right? And what is the formula then, right? The formula says it's going to be e to a t over 2. So t here is this. So e to the sigma square t over 2. N of t, which is sigma squared t, okay, over 2, minus natural log of k, which is k tilde, divided by square root of, right, sigma squared t over 2. And then minus k, which is k tilde, right, n of minus natural log of k tilde divided by square root of sigma square t. Sorry, 1 second, right? Why do I have over 2 here? I say this is sigma square t. So it's just t, sorry. There's no over 2. Okay, like that. Is that okay? So this whole thing right here is this expectation. Now, in case of you losing track of what we're doing, we're calculating expectation of e to minus rt st minus k plus, which we convert to e to minus rt, factor out, that's constant, and then e tilde of this guy. Like that. That's what we're having right now. Okay? And then it's going to be equal to this. So in other words, right, the original expression will be, right, e to minus rt. The constant c is this guy, so let's plug it in. S0 e to the r minus 1/2 sigma squared times t. And then, you know, this thing right here. Okay. Before we, you know, write it down, right? Let's see some obvious cancellation. For example, this and this cancel. The minus 1/2 sigma squared t will cancel with this guy right here. So the first term will be S0 n of that expression. The second, right, will give you, so S0 e to minus 1/2 sigma squared t. So, but actually remember, right, K tilde is K over C. And this is our C right here, right? K tilde is K over C, and this is our C right here. So in other words, right, multiply in, these two cancel, giving you only K e to minus RT times this. All right. Now just need to unravel log of K tilde and we're good. So log of K tilde, right, is log of K over C, which is log K minus log C. But log C, right, is log K, this is C right here, minus log of S0, and then minus R minus 1/2 sigma squared times T, which you see is log of K over S0, and then minus this. Okay. So you see, right, that the first term is sigma squared T minus this. So you got minus log here, right? You got plus R, and then this minus this, right? So the first term will give you S0, all right? N of, so R becomes a plus, and then you got sigma squared T minus 1/2, so you got 1/2. And you got a minus, and then divided by sigma root T. Second term is you get minus, oops, K e to minus RT. And then, right, you just take negative of this. So that's going to be R minus 1/2 sigma squared times T minus log K over S0 divided by sigma root T. So this is exactly your D plus, this is your D minus. So we say there you go. Any question? All right. So again, of course, Black-Scholes formula is something that you should memorize. I mean, yeah, you should do that. You should know the formula if you work in this area. But the proof of it is something you should see once in your life or something. Except, of course, that the idea of the calculation, okay, is super important. So you don't have to do the whole calculation by yourself, but you should try to memorize what's the idea. Trust me, there are several layers of idea in this calculation, okay? That a naive calculation will get nowhere. In other words, if you do this calculation, I think you could work it out, but it will be quite painful. All right. So anyway, so that's that. Now, item B asks us for VT. Okay. So VT is E tilde, right, of, let's say, eta minus RT minus T S big T condition S small t. So this is the call option price at some other time, both besides 0. So what is it, right? Let's see. Remember I said, when you condition on ST, right, you should express S big T in terms of S small t. So in other words, right, S big T, well, it is S0 like this. But it's also S0, sorry, if you start at little t, then you get this. Okay. So then you compare and contrast, okay? You compare and contrast. You see that with V0 is E tilde of eta minus RT S big T condition S0, where this is your S big T in terms of S0. And then here you do S small t, and this is S small t. What you observe is, this Brownian motion, right, is independent of S small t because it's the increment. So in fact, you see that V big T, V small t is just expectation of this. Sorry. Okay. So first of all, pay attention. Your conditioning on S little t. So S little t is known, so it's a constant in that regards, so you factor it out. The rest is independent of S little t because this is a future increment, is independent of the present. So that just becomes an expectation. Okay. But when you compare this with V0, you see that they are exactly the same thing. In other words, it's the same as saying this is a Black-Scholes formula, but you replace S0 with ST, and you replace D plus with D plus of T minus T like this, and then D minus. Okay. In other words, this is the Black-Scholes formula replacing big T with small t, and then, replacing 0 with small t, and replacing big T with big T minus small t. Okay. Where D plus minus will be R minus 1/2 sigma square times T minus T minus log of K over S little t divided by sigma square root of T minus T. So let me say this. All right. So the message for pricing a call option at time little t instead of time 0 is that it's exactly the same as if you were pricing at time 0, except that now you replace, right, 0 with your current time, and you just replace whatever the quantity that's left, the expiration, okay, the expiration, with, this is called time to expiration, okay? So you replace the initial time with your current time, and you replace the expiration with time to expiration. So this explains that most books, or some books, just decide to present you with one formulation. One Black-Scholes formula. They say that the call option price will be ST ND plus minus K e to minus R tau ND minus, where the plus minus is R plus minus, sorry, I missed a plus minus here, 1/2 sigma square times tau minus log of K over ST divided by sigma square root of tau. Okay, like that. That's the one single formula they give you, where it could be confusing, or you could make a mistake if you don't pay attention to what a tau means, or you're not used to tau. Tau is time to expiration, right? Not expiration itself. Okay. So, but if you do this, then this is the only one single formula you have to remember. And as long as you're willing to figure out what tau is for a different t, then you're good. Okay. For example, right, if you have an option, right, right now is September. I mean, actually now it's November, right? And let's say expiry is going to be December, then tau will be 1 month, right? Not 12 months, like December or something. All right. I guess putting it this way is quite obvious, but in the formula, there can be confusion. Any question on this? Okay. So now let's discuss item C, price of put. So in view of this, right, let's just do the price of put option at time 0, for example. So if you do the put option, then the risk neutral pricing says it's going to be E tilde, right, of E to minus RT K minus ST plus. Now, do we have to do the whole calculation again to get to the formula like we did up there?